If you can see the screen, say yes in the chat. If you cannot, say no. So if you can see the screen, say yes. If you cannot, say no. Okay, yes, very good. So yeah, today is the third lesson of exponential and log functions. So we're going to go over homework and then logarithm models, solving equations, and then practice problems. So let's just start with the homework then. So everybody, I'll give you a couple moments to do the homework. Remember that log of x is equal to log base 10 of x. It's called a common log, and ln of x is equal to log base e of x. Right, those are shorthands, basically. Anyways, I'll give you like a couple minutes to do so, and then we'll go over the homework. Okay, let's go over this problem. So, are there any answers or volunteers that would like to solve the problem? Do I have any volunteers? Okay, how about Kaylee? Can you solve the first one?
Okay. Um, so log 5 minus log 2x is equal to log 5 over 2x equals 6. And then we do log to the base of 10. 5 over 2x is equal to 6. So we know that then 5 over 2x is equal to 10 to the 6th power. And so we know then 5 is equal to 2 million x, I think.
Dang, that's a lot.
Yeah. And then x is equal to 0.5 zeros followed by 25.
Yeah. Okay, let me check. Right. So yeah, this is it. Yeah. That's a pretty small answer, but that's how you do it. So make sure you know how the log works, how to change it into exponential form too. Right. Okay, let's go to the next one and try to solve this one. Okay, so let's go over this one. How about someone else this time? How about Andy? Andy, can you solve this?
Yeah, yeah. Um,
Okay.
so, so this one, so, oh, okay. So log, the thing on the left side, if you do, like, it's log 3x minus 1 divided by 2, I mean 3x plus 1.
Okay, so this is just you combine it, right?
Yeah, combine it, and then you divide. And then, so then this thing has to equal to 16. So 3x minus 1 divided by 3x plus 1 equals 16. And then you solve for x.
Okay. Right. So how would you solve for x?
Well, you multiply both sides by 3x plus 1. And then you multiply it out, and then you just subtract the 1.
Okay.
And then you subtract the 1, and then move the 48 to the other side. Then
Negative 17, x equal to negative 17 over 46. So did everybody get this? Are there any?
it's 45.
Okay, 45. Yeah. I messed up there. So yeah, 45. So I think negative 17 over 45. Did everybody get this one? Any questions? Okay, if there are no questions, then let's go to the last homework question, then start our lecture for today. Okay, so let's do this one. 7. Okay. So let's see if that is correct. Log base 6, okay, of 4x plus 8 is equal to 2. So how would we solve this? This one is a bit difficult. So 4x plus 8 is going to be equal to 36. No, never mind. It is not hard. I was thinking about an exponential equation that we'll do later on, but this one is easy. Okay, never mind about that. This one is pretty easy. So yeah, it is 7. Because you move this 8 to the 36, right? And this 28, 28 over 4 is going to be equal to 7. So it's pretty easy. So let's review some logarithms if there are no questions. So does anybody have any questions about what we are going over? If there are no questions, then let's review some logarithm properties. Okay, so I'm going to need some audience participation from this. So let's see here. What exactly is a log again? Well, a log is inverse function of exponential. So it is written log base a of b, and that is going to be equal to log base a of b is going to actually, how about this? A to the b is going to be equal to c, and therefore b is going to be equal to log base a of c. So you see the base of the exponent moves to the base of the log, right? And then the exponent is going to be equal to log base a of c, right? Okay, so that's basically what a log is. If you do want to convert from this back to the exponential form, you have to use this again. So make sure you know how to convert between logarithm and exponential form. That will help greatly when you are solving equations. So let's brainstorm some of the properties of logarithms again. So everybody type in the chat, what are some properties of logarithms that we need to know? Hopefully everybody took some notes last time, so you should know some properties of logarithms. So everybody, let's type in the chat. What are some properties of logarithms? Okay, so I'll give you a few moments to think of some properties of logarithms that we talked about, and then we can start to write them down again. So I'll start with a couple. So this one, our first property here is log base b1 is equal to 0, because obviously 1 is going to be equal to b to the 0. If you convert it to exponential form, it does make sense. Number 2, log base b of b obviously is going to be equal to 1. And so I'm just going to start with those two. And maybe log base b of m is going to be equal to log base b of n if m is equal to n. So here's some 3 properties. I'm going to give you guys a couple moments to brainstorm some more properties here. So yeah, log base a of x plus log base a of y is going to be equal to log base a of x times y. That is one property. So let's write that down. Okay, so let me just get rid of these because these are pretty self-explanatory. Let's write the important ones down because there's a bunch of useless ones that you can just think of. So one we need is log base b of m is equal to log base b of n if m is equal to n. Number 2, someone brought up is log base b of m times n is going to be equal to log base b of m plus log base b of n. So we have a couple more, and that is, let's see here. So log base b to the 1 is equal to 0, yes. K and log base x of a minus log base x of b is equal to log base x of a over b. So let's write that down. That also is very important. Okay, so what else do we have here? We have a couple more that are important. So don't forget, we have a couple important ones. that we can actually derive from the definition. So since c is going to be equal to a to the b, then log of a log base a of c, which equals to b, is going to also equal to log base a of a to the b. So these two a's cancel out. So make sure you know this. Log base a of a to the b is just going to be equal to b. Second one, we can derive that b is going to be equal to log a of c. So what we can do here, a to the b, which is equal to c, is also going to be equal to a to the log base a of c. So as you can see, the a's cancel out again. So a to the log base a of c is just going to be equal to c. So last one we have here that is quite important is how to convert the exponents and move them down. A log base b of m to the p exponent is going to be equal to p log base b of m. So you can basically move the exponent down to the in front of the logarithm. So that's pretty important sometimes. So make sure you have all 6 of these important properties down. And also note the shorthands. Log base 10 of x is equal to log of x. This is called the common log. Okay, and there's also an important one called log base e of x is going to be equal to natural log of x, ln of x. This is called natural log. And these are the ones in your calculator. So if you don't have a graphing calculator, then these are the only ones that are in your calculator. So make sure you always have to convert to these, right? Right, so now let's go over some logarithm models with the decimal scale. Okay. So also, before I do anything, I do want to note some common mistakes that are made. So here are some common mistakes that are made. Right. So these are common mistakes. Right. Okay, so log base b of m over log base b of n does not equal to log base b of m minus log base b of n. It cannot be on a quotient or on a fraction like that. It has to be log base b of m over n, not log base b of m over log base b of n. So a side note here should be log base b of m over log base b of n cannot be simplified. Right? Second of all, you cannot multiply out with logs. So log base b of m plus n does not equal to log base b of m plus log base b of n. So there's no distributive property with logs. So please avoid these common mistakes and check your work. Right. So now let's go on to the decibel scale, one of our logarithm models that we will be touching on today. Logarithm models are not too hard. You're just plugging in numbers, just like the compound interest formulas. So it's basically like a compound interest formula, except for this specific thing. Okay. So, are there any questions? If there are no questions, then I will continue. Right. So, the logarithm model of the decibel scale. The human ear can hear sound over a wide range of intensities. The loudest sound a healthy person can hear without damage to the eardrum has an intensity 1 trillion times that of the softest sound a person can hear. If we were to use these intensities as a scale, we would use very large numbers. Instead, we take advantage of logs to create a more manageable scale for sound intensity, and is called the decibel scale. D, which is the decibels, is equal to 10 times log of I over log base, common log of I over I0. D is going to be equal to the decibel scale, or the decibel level. I is the intensity. This is in watts per square meter. So this is watts over meter squared, right? And then you will have I0, okay, which is 10 to the negative 12th, right? Okay, so are there any questions about the decibel scale here? Okay, if there are no questions, then let's do some problems with the decibel scale. So our question here is find the decibels from a jackhammer with a sound intensity of 3.2 times 10 to the negative third watts over meter squared, and then compute to 2 decimal places. Okay, so I'll give you a few minutes to do this, and then we'll continue on to our next model. Okay, so let's go over this one. This one should not have been too hard. 95.05, let's see. So we take our intensity, right? 3.2 times 10 to the negative third. We got our input in scientific form. So let's just write it like so. So this is the solution. Okay, so 10 times log of 3.2 times 10 to the negative third over, and I0 is given. It's a constant, 10 to the negative 12. So we just need to solve this, right? Okay, so we can solve this pretty easily, and we will get 95.05. Okay, so are there any questions about this? Okay. So the next one we have here is the Richter scale. And that is for measuring earthquakes. Okay. The energy released by a largest earthquake recorded measured in joules is about 100 billion times the energy released by a small earthquake barely felt. Some random guy, not random actually, just a guy. Some guy came up with the Richter scale, right? I imagine his name is Richter. The magnitude of an earthquake M on the Richter scale is given as follows. M, which is the magnitude, M, is equal to 2/3 log of E over E0. So E is going to be equal to, well, first of all, this is the magnitude. E is going to be equal to the energy released. And this is the energy of a small earthquake. And this number is 10 to the 4.4. Okay, so it is another constant. So now let's calculate some problems. So our first problem here is a 1985 earthquake in Chile released approximately 1.26 times 10 to the 16th joules of energy. Okay, and what is the magnitude? Rounded 2 decimal places. Okay, so let's just do this one, right? I'll give you a couple moments to do this one, and then we'll be good. Okay, so let's go over this one. The answer should not be too hard. How about let's call in volunteer this time. How about William? William, could you help us solve this problem?
Okay. So basically, the energy release is 1.26 times 10 to the power 16. So 2/3 log 1.26 times 10 to the power 16 over 10 to the power of 4.4
And
is
that is going to be equal to what? Let's see here. So pull out your calculator. This is actually pretty good calculator practice. Make sure you know how to type it out in the calculator, right? Okay, so let's see. 2/3 log 1.26 times 10 to the 16, right? And that is over 10 to the 4.4. So everybody try to put it into your calculator. See if you can actually get this answer. So the answer should be 7.80. All right, so let's see if you got the same answer. 7.80. So if everybody got the same answer, that's very good. So now let's go on to another problem that we can do with the same scale. So let's do another problem with this. Then we'll move on to the equations. So the question here is, if the energy release of one earthquake right? If the energy release of one earthquake is 10,000 times larger than another, what is the difference in the Richter scale? What is the difference in the Richter scale? If the energy released of one earthquake is 10,000 times larger than another, what is the difference in the Richter scale? Okay. So let's do that one. Okay, so let's go over this one. Answer is 4. So let's think about that for a second. How about William? Can you do this again?
Okay, we just do 2/3 log 2/3 log, let's just say 10 to the power 16 over 10 to the power 4.4 is the first magnitude,
Okay.
and then the second magnitude is 2/3 log 10 to the power of 10 to the power 12 over 10 to the power 4.4. And then after that, we just divide M1 by M2. So,
Right, so it's just M2 minus M1. Or, yeah, the difference in the Richter scale is M2 minus M1. Or, no, it's M1 minus M2, actually. It's M1 minus M2, but I'm sure you know how to do the calculator work, but that's basically how you set it up. This was very unnecessary. You don't really need to do this. You can just say 10,001 here. Right, it's a lot easier. So, yeah, that's how you do that one. So let's now go on to the exponential equations and logarithmic equations. So I'm just gonna walk you through a couple here that are pretty easy. So let's just do 10 to the x. Let's just do a couple here. 10 to the x is equal to log of 9.62. E to the x is equal to 9.62, and 2 to the x is equal to 9.62. So, William, you can quickly do these, right? What is x?
so we
Well, you have to convert it back to what? Oh, right. This one I wrote one wrong. This one is just 9.62. So this one, yeah. How would you do that then?
so that just means it's log 9.62 equals x. So x equals log 9.62.
Okay, so let's just say we found the decimal, blah blah blah, right? And that's yeah, that's basically it. You can always use your calculator, but just keep it in the exact form for now. Now for this next one, how would you do this?
So it'll be x equals ln 9.62.
Right. So yeah, just leave it in exact form. So what about this one? This one.
It'll be x equals log 2 9.62. Log base 2 9.62.
You can't actually do it this way because you can't find log base 2 on your calculator unless you have a graphing calculator. And if you have a graphing calculator, it's still very difficult and tedious every time you do this. So instead, you want to convert everything into log and natural log. So what you can actually do for this one, you don't do it like the other ones. You have to take the log of both sides, right? Take the log of both sides. See the exponent here? Move it down. X is equal to, well, yeah, x times log of 2 is equal to log of 9.62. X is equal to log of 9.62 over log of 2. So this one is easy because the log button is right there on your calculator. So it will be very easy to find this, right? Are there any questions? If there are no questions, then I will continue with some more exponential equations. Okay, so the next one we have here is 5 to the x is equal to 37.81, and 35 to the 1 minus 2x is equal to 7. So let's just do these two. I'll give you a couple moments to do them. Okay? Okay, so let's do these few problems here. So how do we do this? So first one, we take the log of both sides again to get our answer. X is times log of 5 is equal to log of 37.81. X is equal to log of 37.81 over log of 5. Second of all, we take log of both sides again, right? Because if you don't take log of both sides, you'll end up having a log base 35 of 7, which is simply not possible on your calculator. So you have to convert to a common log or a natural log first. So then you can move this down, right? So then 2x is equal to 1 minus 7 over log of 35, and that's over 2. Right. So yeah, you can always do the calculator work on that. So yeah, I'll just leave it in exact form for now because we are running out of time. So some more examples of log equations. We're going to go into logarithmic equations now. So let's just do this one. For this one, right, what you have to do is you have to combine the logs. So log of x minus 15 plus log of x is equal to 2. So what we can do to combine the logs is to multiply them. So we get log of x squared minus 15x is equal to 2. So then you have x squared minus 15x is equal to 10 squared. X squared minus 15x minus 100 is equal to 0. So you have x minus 20 and x plus 5. Therefore, x is equal to 20 and negative 5, but you cannot have negative 5 as an answer. Why can we not have negative 5 as an answer? And that is because log cannot take a negative input. If you think about it, you cannot have a negative exponent, right? Well, the result of an exponent. So no matter a to the x, no matter what x is, it cannot ever be less than 0. So that is why log can also does not take negative inputs, because exponential and log are inverses. Therefore, they are very related. So our next problem here is log x squared is equal to log x quantity squared. So it's a different type of squared here. You cannot distribute. So instead, what you do is you must do this, right? And factor log of x, right, is equal to times log of x minus 2. So what you do is factor the log of x is equal to 0. Log of x is equal to 0, and log of x is equal to 2. So there is a couple things you can have here, and yeah. So when log of x is equal to 0, that means what? It is, hold up a second. Can log of x ever equal 0? Yes, it is 1. So x is equal to 1 here, because log 10 of 10 to the first power is equal to 0, right? Well, no. It's just 1. Log base 10 of 10 to the 0th power, right? Okay, so that does work. I was having a massive brain fart right now. Anyways, tired again, I guess. Anyways, log x is equal to 2. That means x is equal to 100. Okay, make sure you know how to convert between log form and exponential form, because that's how you solve these, right? Okay, so that is it for the log. And yeah, that's all for today. Thank you for listening. I'll see you next class.
Bye, thank you.
Bye.
Yep.
Bye.